at this point, to define Pareto optima is very simple. Let's begin with the concept of a weak Pareto optimum. Weak Pareto optimum. Note the inversion of objectives. We should say that an allocation X is belonging to large A is a weak Pareto optimum if weak Pareto optimum if and only if there not exists another allocation Y such that Y is strictly dominates X. Strictly dominates, not the inversion. In order to have a weak Pareto optimum, there not exist another allocation Y which strongly dominates X. Clearly, it is a definition, but the meaning of this definition will be clear in a moment. On the contrary, we shall say that X, the allocation X, is a strong Pareto optimum, a strong Pareto optimum, if and only if there not exists another allocation Y such that Y weakly dominates X. Also, in this case, there is an inversion of the adjectives, the denominations. The meaning of these two definitions is clear. What is a weak Pareto optimum? Is an allocation with respect to which is not possible to ameliorate the condition of all subjects by means of a redistribution of resources. Why? X is a strong Pareto optimum if it is not possible to ameliorate the condition of at least one subject without worsening the condition of all the other subjects by means of a redistribution of resources. It has denoted by pi W the set of weak Pareto optima, and by pi S the set of strong Pareto optima. It is clear that, generally speaking, the following inclusion holds. Every strong Pareto optimum is also a weak Pareto optimum. Why? Clearly, if it is not possible to ameliorate the condition of one subject without worsening the condition of all the other subjects, it is not possible also to ameliorate the condition of all subjects. Is it clear? So, this inclusion is true by definition, substantial. Problem, but under what conditions also the convex inclusion is verified? Because clearly, if also the second inclusion would be were verified, there is no real need to distinguish between strong and weak Pareto optima. They are the same set, represented as usual in the edge-or box by means of the so-called Pareto set in the case of a pure exchange economy. The problem is, but the converse inclusion is always verified. The answer is no. We shall consider another example for a pure exchange economy, which shows exactly this result. There are some weak Pareto optima which are not strong Pareto optima. Consider another time our two subjects economy. And suppose that their preferences are represented by these two utility functions. In other terms, for the first subject, only the first good is relevant. Is in different schools as this form. Utility increases in this direction. When the quantity of good one increases, no matter the quantity, what the quantity of good two is, utility of the first subject increases as well. While for the second subject, only good two is relevant. And so, in different schools are these. And utility increases in this direction. Remember that for subject 2, coordinate axes are rotated by 108 degrees. Let us consider the following allocation, say alpha, in which all good 2 is given to subject 1, and all good 1 is given to subject 2. Sorry. Is it the contrary? Only a moment. No. It's not at this point. This point. Sorry. I inverted preference relations. Well, sorry, no, another moment. Yes. No. Be patient, is this point. O2. Yes. Well, consider this allocation alpha. Question. It is possible to ameliorate with respect to this allocation the condition of both subjects. Observe, if you move from this point in this direction, you can increase the utility of subject 2, but it is impossible to increase the utility of subject 1, because in order to have that, you must increase the quantity of good 1 which is given to subject 1. This is impossible since all goods are given to subject 1. So this point alpha belongs to pi delta. It's a weak Pareto optimum. It is not possible to increase both levels of utilities by means of a redistribution. But note that if I move from the point alpha to, say, the point beta, what happens? The utility of consumer 1 remains unchanged because it receives the same quantity of good 1, which is the only important good to him. While the utility of subject 2 increases because he obtained a greater quantity of good 2, which is only relevant to subject 2. So the point alpha does not belong to the set of a strong Pareto optimum. In other terms, it is possible, by means of a redistribution of resources, to ameliorate the condition of at least one subject, in our case, the second subject, without worsening the condition of the other subject, the first subject, which obtain exactly the same utility. So, clearly, in this case, the converse inclusion is not verified, because there is an element of pi w, which is not an element of pi. Oh, sorry for the confusion. But the result is clear. Note that this preference relation are regular, continuous, monotone, but they are not strictly monotone. In reality, in order to have the converse inclusion, it is necessary to introduce strict monotonicity, which clearly lacks in this particular case. Now we shall demonstrate the main theorem about weak and strong Pareto optima. If, this is the theory, if for every consumer, the consumption set, as we usually assume, is the non-negative ortant of the n-dimensional Euclidean space, as usual. The relation RH is transitive. We proved a moment ago under what condition you obtain transitivity of this relation. And pH is both continuous and strictly monotone. Then, result, also the converse inclusion holds. And therefore, clearly, our two sets of Pareto optima coincide. There is no need to distinguish between the weak and the strong Pareto optima. Is it clear? I repeat, our assumptions are for every consumer, the consumption set coincides with a non-negative ortant, the weak preference relation is transitive, the strong preference relation is both continuous and strictly monotone, and under all these conditions, you obtain that every weak Pareto optimum is also a strong Pareto optimum. Now, we simply take a weak Pareto optimum that has denoted by X. component, and we must prove that it belongs also to pi s. It is also a strong Pareto optimum. As usual, the proof of this theorem is ab absurdum. Let us suppose that there is another allocation y with these components such that y weakly dominates x. And if this is true, clearly x, it is not a strong Pareto optimum. Is it clear? Moreover, this by definition means that for every h y h x h belongs to RH, and there exists at least a k, such that k, such that yk xk belongs to pk, according to the definition of a strong Pareto optimum. Better, according to the definition of a weak Pareto dominance. Is it clear? Let us concentrate on the situation of this case subject. And let us represent his situation by a graphic. We have that for this subject, yk is preferred to xk. We suppose that this is xk, this is the set of preferred elements, and yk, for example, is here. I put yk on the coordinate axis to make more stringent the proof of the theorem. Observe that yk cannot be equal to the null vector by strict monotonicity. In this case, clearly it is not equal to the null vector. It has at least one positive component. Why? Because by strict monotonicity, it is impossible that the null vector is preferred to any other vector, because any other vector has at least one component which is greater than the component of yk, or the others not smaller. And therefore, it is not possible that yk is preferred to another element of a consumption set. So, this case must be excluded. And, for example, suppose that the quantity of good one, but clearly it's only a possible case, is a positive number. Like in this graphic. I applied the strict monotonicity. This is a fundamental point in which strict monotonicity intervenes. Now let us use continuity of or openness of a preference relation. Since yk is preferred to xk, you can slightly move from yk in any possible direction, and the preference judgment remains unchanged. So, simply move from yk to, say, this point zk, which is simply defined this way. zk1 is equal to yk1 minus a set of positive epsilon, which is the length of this segment, while all the other goods in zk are equal to those of yk. In effect, note that when you move from yk to zk, the quantity of good 1 decreases, while the quantity of good 2, the only other good in this particular case, remains unchanged. Is it clear? But in this way, you obtain by continuity that zk is preferred to xk as well, by the subject k. You obtain this result, which is clear because it is the set pk of xk. Also, zk is preferred to xk, but note, you obtain a preference by saving, so to speak, some quantity, epsilon, of good 1, for example. Is it clear? Now, I can say our assumptions. Now take any other subject, different from the subject K, and consider the bundle ZH, which is defined this way. All the components of ZH are equal to the, to the corresponding components of Y, but the first. Add to the first epsilon on H minus 1. All the other components are equal to those of Y. What happens here? Consider the vector YH, which is, by assumption, preferred or indifferent to XH. And define this other vector, the vector ZH, such that all the components of ZH are equal to the component of YH, but the first, which is increased by what? Epsilon on H minus 1. In other terms, you are subtracting the quantity of epsilon, of good 1, from the subject K. You are redistributing in equal parts, but this is not very important, among all the other subjects. So, the total quantity of good 1 remains unchanged. If you compute the sum of this vector ZH, this is exactly equal to the sum of YH. Clearly, because with respect to the allocation Y, you, I repeat, are subtracting the quantity epsilon of good 1 to the individual, from the individual K, and redistributing in equal parts from all the others H minus 1 subjects. So, the total variation, the quantity of good 1 is minus epsilon plus H minus 1 times epsilon on H minus 1. This can be simplified, and in the end you obtain 0. You have a simple redistribution of a good 1, while all the other quantities of all the subjects remain unchanged. But since this equality is verified and Y was a possible allocation, also Z will be a possible allocation, obviously. All this machinery is introduced in order to prove that in the end Z is not a possible allocation. Now let us compare allocation Z with initial allocation X. we know that subject K prefers ZK, strictly prefers ZK to the bundle ZK to the bundle XK. Well, now let us consider any other subject. What is the relation of ZH with XH? Clearly, ZH is preferred to YH. Why? By strict monotonicity, because ZH contains a larger quantity, good one, while all the other quantities are unchanged. So ZH belongs to pH of YH. But YH was weakly preferred to XH, and since the weak preference relation is transitive, by a well-known theorem proved certainly by Pacini, we obtain that pH of XH is a subset of pH of YH is a subset of pH of XH. Is it clear? This is a theorem proved in consumption theory. If the weak preference relation is transitive, then every Z which is preferred to a Y, which is weakly preferred to X, is strongly preferred to X. But in the end, you obtain that with the allocation Z, every subject, both the subject K and all the other subjects, are better than with the allocation, the initial allocation X. But this is impossible, because X is a weak Pareto optimum, and therefore it is not possible to ameliorate the condition of all subjects by means of a redistribution of resources. Contradiction. And therefore, you proved that also the convex inclusion holds, and so these two sets coincide under these properties, set properties. There is no necessity to distinguish between strong and weak Pareto optima. And this is a standard case of a first degree textbooks or codes. Well, right, and then I shall repeat this proof, which is not a simple one. Our assumption are, for every subject, the consumption set coincides with the non-negative orthant. The relation, the weak preference relation RH is transitive, and the strong preference relation pH is but continuous or open and strictly monotone. The property which lacked in the previous example. Under all these assumptions, we can prove the convex inclusion. Every weak Pareto optimum is also a strong Pareto optimum. Now, take any weak Pareto optimum like this X with component x1 to xh. And suppose, ab absurdo, that there is another location Y such that Y weakly dominates X. This means that X is not a strong Pareto optimum. But this assertion, Y weakly dominates X, means reality by definition that for every subject, YH is